now time has come to study the residue of our function at infinity. To this end, we need to build a Laurent expansion of our function at infinity distant point. And the first question which arises is which direction to infinity we should choose. Because as we see, our infinitely distant circle is split by these two branch cuts into two unconnected arcs. And as we will see later, the answer, the Laurent expansion of the function, will actually depend on the choice of a particular arc. So the question about the residue of this function is senseless because it's ill-defined at infinity. But instead we'll answer another but nonetheless very important question. We'll build the first two terms of the Laurent expansion of this function at these two different arcs. So our first target would be an outer arc. And to find the Laurent expansion of this function, we need to specify a particular direction in which we go to infinity. And of course, the answer will be independent of this choice as long as this direction stays inside this arc. So let's choose the right direction along the real positive axis. Seems to be quite suitable one. So now z equals x. And according to our general schematic, we connect the destination point and the reference point with some contour. This time our destination point is far to the right. So here is our contour. And as before, we trace the changes of the arguments of the constituents of our g function. So number 1 minus z obviously rotates by pi angle in the clockwise direction. As a result, the change of the argument of 1 minus z is negative pi. While the area representing number 1 plus z just sways and doesn't rotate as we go along the contour. So the delta argument of 1 plus z is 0. And as a result, the change of the argument of g function is negative pi. And here we go. F of x now equals the square root of modulus of g of x divided by g of 0 times e2 minus I pi by 2 times 1. And we obtain the modulus of 1 minus x squared under the square root times negative I. Now we can work with this expression from the viewpoint of real analysis. We get rid of modulus sign, interchanging 1 and negative x squared under the square root, and simply build a standard real analysis Taylor expansion for the square root sign. So it's minus I x times the square root of 1 minus 1 over x squared, and we obtain minus I x minus 1 over 2x. And we change x back to z and obtain the first two terms of the Laurent expansion of our function in the outer arc. It's minus iz plus I over 2z. And now let's consider an inner arc between these two branch cuts. Now, which direction to choose this time? Well, the direction along the negative imaginary semi-axis seems to be quite symmetric one, so we'll opt for this. And we parameterize our z number as negative I times y, where y tends to infinity. And now we need to be more careful with the finding out the changes of the arguments of our constituents. For example, number 1 minus z. It rotates by angle almost pi by 2 in the counterclockwise direction, but not quite by pi by 2. As we see, there is some small angle left. Let's denote it delta phi. And you can easily find this angle as the arctangent of 1 over y. So the change of the argument of our 1 minus z number is now pi by 2 minus this angle delta phi. Right? And what about number 1 plus z? You see that it rotates symmetrically, but in the clockwise direction by the angle, and again, not quite by pi by 2, but pi by 2 with the same subtracted angle delta phi. So delta argument of 1 plus z is negative pi by 2 plus delta phi. And we see that fortunately for us, when we determine the change of the argument of g function, these two small angles delta phi disappears from the answer. But in some situations, like for example, if you would have the ratio of 1 minus z and 1 plus z, this change will actually add up and will contribute to the answer. And we will need to be extremely careful because in the answer, additional factor 1 over z will come from this delta phi angle. So, but in this situation, delta argument of g is simply 0. And what we have is f of negative iy now is equal to, as before, the square root of the modulus of g of minus iy divided by g of 0 times e to I 0 times 1. And we obtain the square root of 1 plus y squared. And again, as before, we use real analysis technique to tell or expand this square root. And we obtain y plus 1 over 2y. And then we make a reverse change. Y now is equal to iz. And f of z is now equal to iz minus I over 2z. And we see that our Laurent expansion does look different for different regions at infinity. This is always the case whenever we have branch cuts stretching to infinity. However, if the configuration of the branch cut is such that we have only finite branch cuts, then the Laurent expansion at infinity will have a universal appearance. That is why our next goal is to study the behavior of this function for the finite branch cut. And let's address this question on our next slide.